que ingressou recentemente no corpo científico do IMPA. O Khadim é originalmente do Senegal, foi fazer o doutorado em Trieste, no ICTP, fez um pós-doc em Bochum e agora está começando aqui no IMPA. Ele tem enorme facilidade com línguas, se vocês conversarem com ele, ele já está falando português, mas hoje, para o seminário, ele vai dar a palestra em inglês. E o título é Measures of Maximal Entropy for the Geodesic Flow on Surfaces with Negative Curvature.
Without conjugate points.
Without conjugate points.
Yeah.
Thank you.
Thank you, Marcelo, for the very nice introduction. Thank you also, everybody, for coming, and also for the very warm welcome here in Rio. So the talk is a colloquium talk. So what I'm going to say might be a little, maybe easy for some expert, and at some point it might be annoying, but I apologize for that. I will try to keep it as general as possible for everybody to enjoy. So, as Marcelo said, so my talk is about the measure of maximal entropy. For the geodesic flow. On surfaces without conjugate points. So the title might sound a little technical, but I will try to keep it general by starting with the most common one, which is a surface with negative curvature. So I will start with Mg, a closed Riemannian surface with strictly negative curvature. So which is K. So what I will do in this talk is I will try to first describe the feature of this negative curvature on the geodesic flow. And after I will try to explain how this extend to more general setting like surfaces, a metric without conjugate points. So first of all, we need to talk about what is a geodesic flow. I'm sure most people know, but so the geodesic flow is a flow, we denote it like this, is a flow living on the unit tangent bundle of the surface, where Sm is a unit tangent bundle. And what is this flow doing is, you have here your surface of negative curvature. This flow takes a vector, a point V on the unit tangent bundle. There is a unique geodesic through this point. Let's say we call it CV in general. And this is CV0. And let's say this is CVT. And here I have a vector, and this vector is FTV. This is a definition of the geodesic flow. You take a vector, you draw the geodesic, you flow time t, and that is the image of that vector by the geodesic flow. Now, one of the first consequences of having negative curvature is the well-known Cartan-Hadamard theorem that tells you that the universal cover is R2. M tilde is R2 by Cartan-Hadamard. So to study these geodesics, it's easier to look at the geodesics on the universal cover, which is like a Euclidean space. And to do so, also, we would need to take a compactification of this universal cover. Like there is a natural compactification of M tilde by taking, given VW in the unit tangent bundle of the universal cover, two geodesic rays CV, CW are asymptotic if the distance between CVT and CWT is uniformly bounded in T. And it turns out that being asymptotic here is an equivalence relation in the space of geodesic rays. So being asymptotic is an equivalence relation and the set of equivalence classes is denoted is a boundary of the universal cover and is defined as the set of equivalence classes. Yeah. So now I need to introduce a very useful function for what I'm going to do next, which is called the Boozman function. It's a very simple function to define. So given V in SM tilde, BV is a function from M tilde to R that is defined by, BVX is a limit when t tends to infinity of the distance between CVT x minus t. One can wonder about the fact that this function is well defined. Actually, it is well defined in a more general setting, not only in negative curvature. Also, if you assume some more general, like if just the geodesics are minimal in the universal cover, you have this function is well defined. And it turns out that BV is C1, is even smooth in the case of negative curvature by Eschenberg. So what is the use of this function? This function is used to, okay, let's see first what is this function doing. I have here my geodesic here. This is V, this is CV. I take another point X on the universal cover. You see this point X, let's say this is CVT. You take this geodesics that is joining CV, this is CVT to X. This geodesics is converging to a geodesic at the limit that is asymptotic. This guy will be asymptotic to CV. We'll say in a bounded distance. And this leads us to define the set of geodesics that are asymptotic using this Boozman function. Namely, we define the horosphere at V to be the level set. Here I should put some other notation, like there is a point CV infinity, where CV infinity is a point in the boundary, which is associated to this geodesic. So if one looks very well the definition of the Boltzmann function, we can see that it satisfies this property, like bvx minus b. Let's say f tilde v is the lift of the geodesic flow in the universal cover equals minus t. Because here if you plug x is cv0, you just translate this distance is t. So this gives the invariance of the horospheres. By geodesics. Mainly this is what is happening. I have here the compactification of my universal cover. I have a point at infinity. Let's say I have a geodesic here. This is CV, and this is CV infinity. This is a geodesic. Let's say this is a vector V. This is a horosphere at V that is attached to the point CV infinity. And if you flow these geodesics, but this horosphere by geodesics, you get the invariance, you get the other horospheres. Like if this is HV, C infinity, I would just simplify this notation, call it psi. Okay. So, and let's say this point is CVT, and this horosphere will be F tilde T V C. There's more. So from here, there is a mapping. There is a map between the horospheres HCV to HC F tilde TV by just taking geodesics. Here you have at the horosphere, you take the geodesic that is orthogonal to the horosphere. It leaves invariance. You go to the next horosphere. But the most important thing is the Jacobian of this map satisfy a very well-known equation, which is a Jacobi equation. The Jacobian of this map satisfies this is known as the Jacobi equation. So you see very well that if in case of negative curvature, you see the horosphere that are contracting, exponentially contracting. So this is one key feature of having a negative curvature. Exponential contraction of horospheres by the geodesic flow. So this will lead to the notion of this geodesic flow being a Nosov. Like from this horosphere, you can define a manifold on the unit tangent bundle by just taking, let's W tilde in the universal cover. You take this point, X, and where X is in H. So actually I did not say, but the flow, the gradient flow of this BV function, this Boltzmann function satisfying this So the flow lines of the gradient of these functions are geodesics. So you take the tangent to the inner tangent to the horosphere, and the base point is define you a manifold on the unit tangent bundle of the universal cover. We can call it stable by the fact that what I just said, I have exponential contraction, so I see these manifolds are contracting by the geodesic flow. So this implies that the geodesic flow is Anosov. Is Anosov meaning, in the general setting of Anosov, this is what you have, the tangent space of your manifold, which is a unit tangent bundle, splits into 3 subbundles that are invariant. This is a flow line, and this is an unstable bundle, which is defined by the stable of the inverse of minus v. And the differential of the flow is contracting these guys in the future and contracting these guys in the past. So, so this class belongs now to a bigger class of system that people have been studied a lot in the last, called the Anosov map, Anosov diffeomorphisms, and so on. And for these maps, or for these flows, we have 2 interesting measures that people are interested in studying. Namely, for the geodesic flow, we have the Louisville measure, for people who are more familiar with contact geometry, the geodesic flows being a contact flow, it lives invariant to one form. It lives invariant to one form, ft star of alpha equals alpha, and alpha is contact. And the Louisville measure, which is a volume, is defined to be this volume measure. So people are interested in many properties of this measure, for instance, about ergodicity, about mixing, and k-mixing, or other statistical properties. And so far, in negative curvature, it was known by Hoff, M is ergodic. I don't think I need to define what ergodicity means, but it just says that you cannot decompose the system. The system is kind of irreducible in the measure theoretic sense. Like you cannot have 2 invariant sets that are meaningful with respect to this measure. Basically, that's what ergodic means. And actually, M is exponentially mixing, or the flow F is exponentially mixing with respect to M. For surfaces, so this can follow from a result by Dolgopiat in 1970. And also in the general case of contact annals of flow, it follows by a result by Carlangelo Liverani in 2004. By exponential mixing, I mean this: if I integrate FG, oops, I should not use F. Is a G. This is less than C times exponential of lambda t minus lambda t, where lambda is positive. Yes, yes. Yes. DM, yes. So by exponential, it's just the rate of convergence of this guy. Yeah, actually, this measure also, it generalizes to now what is now known as the SRB measure for general systems. Like, if you just assume you have enough hyperbolicity, you can define a measure that is a generalization of this one, which is called the SRB measure, Sinai-Rowell-Bourne measure. And also people are interested in many properties of this measure, ergodicity, mixing, and actually, like there are conjectures saying that mixing for this SRB measure is generic, is open and dense in the space of Anderson flow. And myself and Oliver Butler last year, we had a result on this, proving this conjecture in the space, at least in dimension 4, in the space of volume preserving Anderson flow. But that's not the subject of this talk today. So I wanted just to say there is this measure which is interesting, and there is another measure, which is a measure of maximal entropy. Yeah. So the measure of maximal entropy. So first of all, what is the entropy? The entropy is kind of a measure of the complexity of the system. Like if you look at the system, you fix a time, and you fix a scale epsilon. Let's say I fix time t, I fix the scale epsilon. I look at the number of indistinguishable orbits up to time t at scale epsilon. If this number is exponential, the flow has positive entropy. If it is sub-exponential, it has 0 entropy. So it's basically looking at the complexity of the system. So the entropy is defined as follow. The topological entropy of the flow. So this, oops, I should say, no, sorry. And the Lume soup, when t goes to infinity, of 1 over t log. So this is a kind of a very involved formula, but it's just what I'm saying. This is the cardinality, the maximal cardinality of the indistinguishable orbit up to time t at scale epsilon. And you take log of this, you divide by, oops, I should put t here, yes, where lambda epsilon t is the maximal cardinality of epsilon t separated set. Now to this topological entropy, there is a nice formula which is called the variational principle that expresses the topological entropy with respect to the measure theoretic entropy, saying that variational principle it says that the topological entropy of the flow is given by the supremum of the metric entropy, where mu is in mf of Sm, where mf Sm is a set of Borel probability Ft invariant measures. And Hmu is a measure theoretic entropy, which kind of tells you, like, if you take a partition with respect to this measure, and you take the diameter of this partition going to 0, you evaluate this quantity. You take the measure times the log of the measure of the partition element, and you take the limit when the partition element, the size is going to 0, you get the measure theoretic entropy. Now, there is something like the measure mu max that realizes supremum is called measure of maximal entropy. Yeah. So this is another measure of interest beside the SRB measure or the Louisville measure. And in general, these two measures are different in general. Actually, there was this theorem by Katok that the Louisville measure is a measure of maximal entropy if and only if K is constant. And this is conjectured in higher dimension that if you have this, so you should have a symmetric space. That's an open problem. So what are we interested in this measure? In this measure of maximal entropy. So you can see that this supremum is usually, you have the upper semi-continuity of this function with respect to the measure. It always gives the existence of the measure of maximal entropy. But we're interested in the uniqueness of the measure of maximal entropy and some other properties like mixing or the support of this measure and so on. So that's what really my interest was in this topic, mainly knowing what is the support of this measure. Is it supported in this Borel set? Is it mixing? Is it ergodic also? Yeah. So what is known about this measure? I mean, for negative curvature implies Anosov. Unique MME. And for non-positive curvature, so there is also a unique MME. This was proved by Gerhard Knieper, who is one of my co-author here, in 1907. And people have been trying to generalize now this negative, non-positive curvature assumption. So his proof, like, it's non-positive curvature for surfaces, but in higher dimension, it's non-positive rank 1 manifold. So how do we generalize this? First, there is a slight generalization using no focal points. No focal points. This is actually recently done last year by Catherine Gelford and Rafael Ruggiero, and also independently using different method by, I should remember the names very well. Okay, here. So, Gelford and Ruggiero. 2018, and also by Cheng, Gao, and Park, also in 2018. But they just have the uniqueness. They don't study the support of this measure or the other properties like mixing of this measure. I mean, being unique is also ergodic, okay? So ergodicity is not a big deal here. No focal points, what does it mean? It means, so I erase the Jacobi equation. So the Jacobi equation, remember, it was this. No focal points. It tells you that if you have a vanishing Jacobi fields whose derivative is non-zero, the JT is increasing. It cannot decrease. So basically, this is what it's saying. I like to draw this picture. So this is my geodesic CV. So the Jacobi fields is just growing. Like if you look at Jacobi fields along this geodesic. So if it does this, that means that this is a focal point. Basically, JT is increasing. Yeah. So yeah, they have the uniqueness of the measure. I forgot also to mention that Cheng, Kao, and Park also have the equilibrium states for general, like Holder continuous potential here. But that's also not the point of what I want to say today. So what do we do now? We generalize it to no conjugate points. No conjugate points, it's this, what it's saying is that you cannot have a Jacobi field that start being 0 and also 0 again. So if you have this, that means that these 2 points are conjugate. Like this is a Jacobi field. You cannot have this. That's the condition. So this is the result we have in this setting. Is by Climenhaga, who is in Houston, Gerhard Knieper, who is in Bochum, and myself. This is on the archive just like 2 months ago in March, yes. So what do we prove is that if MG is a surface with no conjugate points, then F, the geodesic flow, has a unique MME mu max. And moreover, we say that mu max is fully supported. I will say what is this is fully supported. Is given by, I will also say what this means, by limiting distribution along closed orbit. Along closed orbit. And F is mixing with respect to mu max. F is just mixing. We don't have any rate of mixing with respect to mu max. Yeah. So by fully supported, I mean that it gives positive measure to the Borel open sets. Every open set has a positive measure. Is a limiting distribution along closed orbit is that if you take Dirac delta along closed orbit of period less than t, and you take t going to infinity, this distribution is converging to a measure of maximal entropy. And also the flow is mixing. So yeah. First of all, I should say how this is done in the negative curvature. And what are the conditions, like what are the properties that we need to extend to this more general setting. So usually the proof is based on 2 main facts that I will break down into pieces step by step. There is what is called the specification plus expansivity. What is specification? Specification is just saying you give me pieces of orbits randomly on the space. There is one orbit that shadow every piece and spend a fixed amount of time in these gaps. Like you can have one orbit that stay close to here, go somewhere, do this, and then this. This is what specification means. I will say later how to use this. So specification, if you give me pieces of orbits randomly, there is one orbit that shadow every piece and spend a fixed amount of time in the gaps. And expansive means that for every epsilon positive and x on the unit tangent bundle, this set, the set, I was calling it V here. The set of W says that the distance between FTV, FTW is less than epsilon for all t in R. This is a subset, is a piece of the orbit, is a piece of the orbit of V, of F minus epsilon, epsilon V. So this is saying that if two orbits are staying together for all times, they are the same. So obviously, this property breaks down when you put some positive curvature, because if you think of like the surface having some flat strips here, here you will have these closed orbits that stay at a bounded distance. So here you don't have expansivity. Whereas in the Anosov system, in the negative curvature case, expansivity follows directly from the splitting using this stable and unstable manifold. Okay? So in the general setting of no conjugate points, these two properties are properties that one needs to generalize. So first of all, I would just tell you a little bit how this uses hyperbolicity, how the specification is given by the hyperbolicity. By hyperbolicity, I mean the existence of these stable and unstable manifolds, the existence of these invariant bundles. So let me just do it for the baby case, and this illustrates the general case. Like, let's say I have, so yeah. So first of all, for specification, there are two parts. It splits into two parts. There is shadowing plus transitivity. Shadowing means that you give me pieces of orbit where the endpoints are nearby. No matter how many of them you give, I can find one orbit that shadow this. And transitivity means that you have a dense orbit. Once you have this and transitivity, you can easily create this. So I will just explain very briefly how to get this shadowing from hyperbolicity and to see how this, you cannot get it in this case, for instance, when you have the flat strip, because you don't have enough hyperbolicity there. So this is the baby case. Let me just suppose that I have a hyperbolic, let's say even a map, where I have just two splitting. One is exponentially contracting, one is expanding. If you just look at, if you have 3 points, let's say x1, x2, and x3. To get the shadowing, you need to suppose that f of x1 is close to x2, and f of x2 is close to x3. Let's say you want to find one orbit that shadow this whole sequence. This is just a baby case, but it illustrates what happens in the general case. So the thing is, if you take x1, it shadowed this orbit till here, but after, the gap might increase. So what you can do is if from here you take the unstable manifold of this guy and the stable manifold of this guy, they intersect at a point, let's say y, I define x tilde as f minus 1 of y I know being on the unstable manifold of this guy, if I pull it back, it gets close to x1. So it is always in this neighborhood. Being in the stable of this guy, when I iterate it forward, it gets close to f of x2. So this is f of y, which is f squared of x tilde. So doing this, having the existence of this manifold and the local product structure, you can have shadowing. So it follows local product structure means that if I take stable and unstable, they always intersect at one point. So this property also uses highly the hyperbolicity, which we don't have in the non-conjugate point setting. So what do we do in this case? What we do is we can have specification, but not at a very small scale. Because when we talk about this specification, you need to shadow at any small scale. But if I allow the scale to be big, I can always shadow by using this. Let's say this is the compactification of the universal cover. Let's say this is a geodesic with respect to the metric of negative curvature, with respect to my metric of no conjugate points. I know that the surface being of higher genus, it admits a background metric of negative curvature. So there is a background hyperbolicity that you have here. And there is a kind of a Morse comparison that tells you that any geodesic in this negative curvature is bounded, stay bounded to another geodesics in the negative curvature. Let's say this is my metric G, okay, no conjugate points. There is another guy, G0. G0 is a metric, it's a background metric of negative curvature. So what you basically do to get specification is every piece here, it corresponds to another piece of negative curvature. And you can use the negative curvature being Anosov to shadow these guys. And you can go back to the metric of no conjugate points using the Morse comparison. But the problem being the scale is big because you don't have control like on this distance. So that's, we have specification at some scale R, which might be very large. We don't know. Also, there is this problem of expansivity. But the thing is, we know in some parts you have expansivity, like you have some vectors that are really expansive. So basically, what we need to prove is that the non-expansive set doesn't carry any entropy. The entropy in the non-expansive set is 0. So the entropy is on the expansive set. And it's easy for surfaces to see that the non-expansive set doesn't carry entropy because if you have positive entropy of an invariant set, there is a Ruhl formula that tells you that you have always this positive exponent. There is always a positive Lyapunov of exponents. And if you have positive Lyapunov of exponents, you have these Pessin manifolds, stable and unstable manifold. And once you have those manifolds, you are expansive. So that proves that this doesn't carry any entropy, the non-expansive set. So we call it the gap. We have entropy gap. And from here, we use a result. We have these two, entropy gap. That there is a result by Vaughn, Climenhaga, and Dan Thompson, that tells you that if you have specification at some scale R, and you have entropy gap. Entropy gap also there is at scale epsilon, let's say, because it depends on how do you define to be expansive. a vector is expansive with respect to epsilon. Okay, there is a scale epsilon that you fix. So Vaughn, Climenhaga, and Dan Thompson in 2016, they have a refined results they have a refinement of this proof that specification and expansivity implies the uniqueness of a MME. Now they have a result that specification in a good set of the manifold and also entropy gap at some scale implies also uniqueness. Like R being bigger than much bigger than epsilon implies unique MME. Yeah. Here there is a small technicality because if epsilon is big, you can never achieve this. But what we do is we go to a finite cover to the manifold to make the injectivity radius so that we can always guarantee this happens. So this is how basically the proof of the uniqueness, it uses the original proof of Vaughn that uses specification and expansivity, the refined version by Climenhaga and Thompson. Specification in a good part of the manifold and also entropy gap. Now there is a last part about this measure being supported along, like given by limiting distribution along closed orbits. This is basically done knowing the asymptotic rate of these periodic orbits. So for negative curvature, there is a well-known Margulis estimate that gives you the exact asymptotic rate of the periodic orbits, namely the number of periodic orbits of period less than t. This is approximatively, H is the topological entropy. This is known as the Margulis estimate that you have in negative curvature. And so we can have something similar, slightly similar. In the space, in the setting of non-conjugate points, we can have that the limit of 1 over t, the log of, let's call this pt. This is h. How do we get this? Is actually you can characterize the closed orbit just using the fundamental group of the manifolds. Like the closed orbit are axes of the elements of the fundamental group. These are invariant by the element of the fundamental group. So the manifold having the same fundamental group, you expect to have the same asymptotic rates of the number of periodic orbits. There's modulo some technicalities, that's the idea. Relying on the background metric of negative curvature and knowing that they have the same fundamental group and these closed orbits are characterized being axes of these elements of the fundamental group. And yeah, so now this part, if you have this, there is this is not very difficult. It is actually in some textbook, limiting distribution along closed orbits. Gives MME. It's basically because, when I say the number of closed orbit, I mean the number of homotopy classes of them. So if you know this number of closed orbit, it's basically kind of, you know, the number of epsilon separated set. It's basically, you have them basically because each closed orbit will kind of carry one epsilon separated set. And yeah, basically it's not very difficult actually, this part. So from this, you have that taking limiting distribution along closed orbit gives you MME, knowing it is unique, so it is the only one. Okay? So there is another part for this being fully supported. For the measure being fully supported, we use something completely different, another construction of the measure, which is based on the so-called Patterson-Sullivan construction, which was done by Gerhard Knieper to prove uniqueness of MME non-positive curvature setting, basically what you do is this. You prove that you can project this measure on the boundary. The measure that you have on the unit tangent bundle, you can project it as a product measure on the boundary. And this product measure is fully supported on the boundary. And being fully supported on the boundary, that means also that if you take a point, if you take two vectors, like an open set on the unit tangent bundle is just given by a point and two vectors with an angle, they go to two different points. And you will have this guy have positive measure, so the measure on the unit tangent bundle also will have positive measure. So this basically relies on the fact that you can redo the Patterson-Sullivan construction in this setting of non-positive, no conjugate points. And the proof of mixing, it uses actually something completely different. Maybe I won't talk about it. I will just say, what are the key properties of everything that I have been doing here? There is one very important, which is a background hyperbolicity. That I have a background hyperbolicity that I can rely to get specification, though at large scale I can get it. And also I have the asymptotic rates of these closed orbits, so that's a key point. There's also another key point, which is called the divergence property of geodesic rays. This property that I just said. At a point, if you have two vectors, these geodesics are going to diverge. This is known for surfaces by Green. And in higher dimension, it's still open. Nobody knows if this is true or not. So to extend this result to higher dimension, one needs this assumption that you have divergence of geodesic ray. Because remember, if actually you don't have this divergence property, even the horospheres are not well defined. Like they don't give foliation to the universal cover. So this is something key that we cannot avoid in higher dimension. And the background metric of negative curvature is also some key property. And also there is a gap. There's a gap. In higher dimension, the proof of the gap that I just sketched doesn't work. Because what I said is, if you have positive entropy in the non-expansive set, you have positive exponents on surfaces, so also I have a negative exponent, so I have stable and unstable manifold. But in higher dimension, you don't know. You might have many directions. You don't have any control on that. So in higher dimension, we need a gap, an entropy gap. We need a background metric of negative curvature. There's also another slight technicality to generalize this, which we think it's not very necessary, that the fundamental group of the manifold is residually finite. That allows us to get this property because as I said, if epsilon is large, bigger than the injectivity radius of the manifold, you can never get this because the non-expansive set is the whole thing. So you want the manifold to be big. To be able to make the manifold big, we go to a finite cover. Being able to go to this finite cover with arbitrarily large injectivity radius is given by the fact that the fundamental group is residually finite, which is known for surfaces, but in higher dimension it is open. Like there is a conjecture that having a background negative curvature implies that the manifold is residually finite, but yeah, nobody knows so far how to deal with this. Yeah. So basically, this is what I wanted to say. So I'm open for questions.
Thank you very much, Khadim.